We're heading into an El Niño season.
A warning from meteorologists this morning: a super El Niño could arrive in the next few months.
And if it does, it could bring with it the threat of droughts and heat waves.
Alarming news items like these is what we can expect when El Niño returns. And it occurs here in the Pacific Ocean. And that is one of the biggest oceans of the world, bordering North and South America, Australia and Asia. And everything that happens here in this ocean has a big impact on the weather and everything related to it. Think about extreme flooding, droughts and heat waves. From our special studio here on the Pacific Ocean, we will explain to you in detail how El Niño works. For the discovery of El Niño, we have to go back a few centuries. It were the fishermen in the coastal villages of South America who were the first to notice that their coastal waters once every couple years became warmer than average. Usually the upwelling of cold and nutrient-dense water was taking place here. When the water became warmer than average, their catch was decreasing, and this was a major threat for the food security of these small communities. The locals called it El Niño, meaning the Christmas child, because this usually happens during the festive Christmas period. La Niña is the counterpart of El Niño, and when this happens, the ocean water around the equator of the Pacific is a bit colder than average. What causes the difference between El Niño and La Niña, and how can we predict the transition between them? The main reason why El Niño and La Niña are a bit complex to understand is the interaction between the ocean and the atmosphere. There are a lot of factors to consider, they all interact with each other and they also amplify each other. And since that first discovery of the fishermen in the coastal villages of South America, the next steps in the unraveling of El Niño were made by science. Nowadays, science is still occupied with researching the effects and impacts of El Niño we can expect in the future with global warming. One of these founding fathers of El Niño is the scientist Gilbert Walker. His research project between 1903 and 1923 focused on the changes of air pressure and weather patterns in the Indian and Pacific Ocean. And he noticed that places with convection, with rising air motions, recorded a lower mean sea level pressure, whereas other places with descending air motions recorded a higher pressure. We can see this in the graph in front of me on the desk. Gilbert Walker called these changes in air pressure the Southern Oscillation, and this index, the Southern Oscillation Index, SOY, is still used nowadays. The difference in air pressure between Darwin in Australia and Tahiti in the middle of the Pacific Ocean is calculated. The investigation of the changes in air pressure resulted in the discovery of a bigger circulation, and Walker described this with the concept of the Walker circulation. In this Walker circulation, we observe ascending motions with clouds and rain in the Western Pacific, whereas the Eastern Pacific is characterized by dry descending motions. On our Earth, we have similar circulations. Think about the Hadley and Farrell cell in the global circulation, which you can see in the globe in front of me. These are oriented in a north-south direction, whereas the Walker circulation has a west to east direction. Gilbert Walker was responsible for another important discovery, the North Atlantic Oscillation. And here we calculate the pressure difference between Iceland and the Azores. And we distinguish NAO positive and NAO negative weather patterns. There was one thing. Gilbert Walker was mostly focusing on the atmosphere, but he didn't pay too much attention to the ocean. With El Niño and La Niña, everything is connected to each other, so the ocean has an impact on our weather as well. Think about the warm Gulf Stream, for example, that is responsible for rather mild winters in Western Europe. The Gulf Stream begins in the Gulf of Mexico and brings warm water to the northern parts of the Atlantic Ocean. And this Gulf Stream is part of a global conveyor belt of ocean water with warm shallow currents and deep cold currents. The following steps in the unraveling of El Niño were made in the 1960s by the Norwegian scientist Jacob Bjerknes. Because in the 1960s, the first weather satellites were launched, and we could install advanced weather stations on various islands spread over the Pacific Ocean. And all this new information enabled researchers to make connections between the differences in air pressure and the ocean temperature. And they figured out that little changes became bigger and bigger, and also the impact became bigger. And this is what we call a positive feedback. And in this specific case, the Bjerknes feedback. We begin by describing a so-called neutral situation. The winds around the equator are almost always blowing from the east to the west. And sailing ships made use of these winds in the past as well. And their name, the trade winds, is related to that aspect of our history as well. The trade winds blow the relatively warm surface water towards Indonesia and Australia. But the removal of water has to be compensated, and that is where the upwelling of cold and nutrient-dense water in front of the coast of South America is coming from. The energy from the warm surface water is transferred to the lower layers of the atmosphere in the Western Pacific, and this results in the air warming up. The warm pockets of air start to rise because of the lower density. Convection is initiated, and this results in the formation of clouds and eventually rain showers or even thunderstorms. Descending air above South America is the compensating mechanism in the Walker circulation. The trade winds are the connection between these ascending and descending motions. The trade winds become stronger when the temperature difference and thus the pressure difference between the Western and Eastern Pacific is becoming bigger. Indonesia and Australia can even report a slightly higher sea level due to the stronger winds. A warmer ocean will result in stronger convection with heavier showers. The ocean water that is being pushed away wants to return to restore balance. You can compare this with the movement of water in a bathtub when you step out or into the water, and the liquid is displaced. The upwelling of even colder and nutrient-dense water is accelerated in the coastal regions of Southern America. La Niña is here. The transition to El Niño begins when the trade winds start to weaken. The wind can even make a 180-degree turn to become west to east oriented instead of the common east to west direction. The temperature of the ocean around the equator starts to increase as well, because the warm surface water is not being pushed away anymore to the Western Pacific. The water can be 3 degrees warmer than average in a powerful El Niño phase. Regions where the weather is usually calm and dry will experience more rain after El Niño has begun. Upwelling of cold and nutrient-dense water from the deep ocean is on hold, and this is exactly what the fishermen feared in the past. The circle of the Walker circulation, as we mentioned earlier, is moving. The strength of El Niño can be determined by investigating how far the Walker circulation is moving towards the east. A weak El Niño event has warm ocean water and showers approximately up to the international dateline, whereas a stronger El Niño event has warm ocean water and strong showers up to the coast of South America. And the Southern Oscillation Index is a numerical value to indicate the strength of an El Niño or La Niña event. El Niño is not only affecting the weather in the Pacific. Regions elsewhere with little rain can experience heavy showers, for example, and vice versa. Problems caused by heavy flooding or a deficit of rainfall can differ per continent or even per country, depending on whether we have an El Niño or a La Niña period. And you can see this in the map behind me. The first effects after El Niño has begun can be found in the tropics. The ocean water and the air temperature are becoming warmer, and the global temperature responds to this as well. Combined with climate change, this is leading to the warmest years on Earth ever recorded. Furthermore, El Niño is also connected with the reduction of hurricanes in the Atlantic Ocean. And the opposite is true for La Niña, when we can expect more Atlantic hurricanes. The effects of El Niño and La Niña generally reduce with the distance to the Pacific. Australia, for example, which is rather close to the Pacific Ocean, can expect severe drought when El Niño has begun. Europe, on the other hand, located further away from the Pacific, has a slight signal for a bit more rain during spring, but these changes are rather minimal. Improvements in weather forecasting and climate models have enabled us to predict the transition between El Niño and La Niña about 6 months in advance. And just as in the past, other indicators that a change is imminent can be found in measurements of the ocean and water temperature. As long as the global circulation on our Earth doesn't change, the cycle of El Niño and La Niña will keep repeating itself. One of the most frequently asked questions is what is the effect of climate change on El Niño? In our current climate, an extreme event occurs about once every 20 years. But with global warming, the return period of such an extreme event will be reduced to 10 years. El Niño is an addition to the impact of climate change we are already facing. And if it becomes even more extreme in the future, it could lead to major disruptions and extreme weather, affecting a majority of the Earth's population.